All right. Good evening, and thank you for joining us to another NYJavaSIG event. We want to thank you for being here with us, and we want to know more about you. Please use the chat and let us know where you're from. Is that your first time at NYJavaSIG? We want to know more about you. We're very excited to have this presentation today with Ron Pressler, the tech lead of Project Loom. And we want your participation in the event. Please use the chat and ask questions, as many as you want. We appreciate your questions. We want you to participate. Before we start, I want to call Frank, the NYJavaSIG chair, to say a few words. Frank?
Thanks, Rodrigo. And thanks, everybody, for joining this evening, this morning, this afternoon, wherever you are in the planet. I wanted to, normally, before when we start a meeting, we've had some really cool pre-meeting bits from Gene on getting to know more about Java and did you know code samples, which is really, really cool. And we also thought another cool thing to do is get to know the NYJavaSIG community, especially the New York JavaSIG leaders. And I think I've mentioned this before, but the past 4 or 5 years, the success of the JavaSIG is really due to our group of JavaSIG leaders who've volunteered their time to spread the gospel about Java. So we thought we'd start with a couple of our JavaSIG leaders and just find out a little more about them. And we've asked Gene Boyarsky and Barry Bird, both being authors, Java authors and other authors, so to and find out more about them and about their books. So let's start off with Gene. So Gene, let's talk about the books that you have authored.
Did you know I've written a bunch of Java cert books? The most recent is the OCP Java 11 Combined Study Guide, which is published both individually and as 2 books in one. You can see how thick the 2 books are, as thick as I am. So lots of reading and lots of opportunities for learning.
That's cool. And then Barry, your book or books. And Barry, if you need to.
There we are. Okay. Yeah. Hey, look, here we are. Java for Dummies. Got a couple of many books in the Dummies series, which means that most of the people here probably aren't interested in picking them up, except to read the jokes in the books. But if you have a friend who needs to learn Java from scratch, that's a good place to do it.
So Barry, I've mentioned this at when we had meetings, face-to-face meetings, but you've written more than just one book. I mean, how many books have you written?
So I've written 11, and that doesn't include different editions. I think I counted, the last time you asked was about 22, if you count the various editions of different books. That's 11 like books, and Java for Dummies is going into its 8th edition soon. So add up all those numbers and you get 11 editions of various books.
That's an insane amount of books that you authored, and just totally insane.
Well, it's not Stephen King. Don't worry about that.
And this is in addition to your teaching responsibilities, right?
Yeah, this is not my day job.
So you've been teaching at Drew University for quite a while, and I mean, how many students do you think you've had at Drew?
So it's about 60 per semester. So that's about 120 a year. And I've only been teaching for 40 years.
That's all?
At Drew, yeah. So yeah, it adds up. I've met my students, former students' children, and I think I've met my former students' children's children, although I'm not sure about that. Memory fades.
Wow, so there's just an incredible amount of developers that you've turned into strong programmers and architects, and that now work for companies and have developed all kinds of cool software. That's just amazing.
Yeah, I get a lot of good feedback from email on the web, and I really appreciate it when I get it.
Yeah, that's fantastic. So Gene, so you're a Java champion, and can you tell me a little bit about the Java Champion program?
Sure. The Java Champion program is about people in the industry or wherever who are spreading knowledge about Java, whether it's from running user groups or writing books or speaking at conferences or writing blog posts, but they're having an impact on lots of people and spreading Java around. And it's really awesome to be in that group.
It's fantastic. And I know that there's about 320, I think 322 Java champions.
About that.
322 Java champions. And I think, where did I read recently? There's 10 million, a conservative estimate, there's 10 million Java developers. So that's certainly an elite, it's an elite group. That's, let's see, that's 0.003 of 1%. That's an incredibly elite group. So that's a really cool accomplishment, Gene. So it's good. So that's fantastic. And speaking of Java champions, there were some recent Java champions, and I just wanted to have a shout out to them. So this is the international Java community. It's not just the JavaSIG, the New York JavaSIG. So Hong Lee, congratulations to Hong Lee, is now a Java champion, and congratulations to Maria Arias de Reina Dominguez. So congratulations, Maria and Hong Lee, on being Java champions. There were 3 inductees last 2 weeks ago. So I'm really especially honored, and I'm really thrilled to announce that one of our own in the New York JavaSIG was named Java champion. So I want to congratulate Professor Barry Bird for being voted Java champion. It's well deserved, Barry. Congratulations.
Oh, congratulations.
I want everybody to know that this is not a fake. This is a.
No, you're right.
We managed to surprise you.
So congratulations, and we got you something, Barry. So
Oh, wonderful! I love that.
For those out there,
we also created a virtual card for Barry. The group greeting card is in the YouTube chat. Please sign the card by the end of the evening, and then it will be sent electronically to Barry.
You could just
Fantastic.
reach out of the
So again,
screen and hand me stuff.
Congratulations again, Barry.
Oh, thank you.
So let me turn it over to Rodrigo.
All right. Thank you, Frank. Barry, congratulations.
Ooh.
We're very happy for you. Well deserved. I'm impressed with the number of people here in the chat typing that many of them read your books and Gene's books. I have Gene books here with me as well. And I'm waiting for yours. We talked before.
I'm on it. I'm
waiting for yours. Now I'm going to be the first one to have your signature on a book after you've been nominated a Java champion.
and don't forget to pay me with a Shake Shack meal.
Yeah, that's a deal. That's a deal.
Okay, all right.
And Gene, I was reading here in the chat, Gene, people that they read your book and did the certification, and they said that after reading your book, it was a piece of cake. So congratulations as well on the good work. We are surrounded by amazing people here at the NYJavaSIG. I want to thank you. There are people from Toronto, Amsterdam, New York, Argentina, Sydney. Wow, thank you. Bangalore, Jersey, Denver, Turkey. Thank you everyone for being here with us. I would just want to say, please follow us if you're not following us yet on Twitter at NYJavaSIG is where we are more active. So all of our events we announce on Twitter. Here's our website, javasig.com. Please go there. Everything you want to know about Java, we'll be posting there. Our events are there. And we're going to find links to recordings of our previous videos as well. One more announcement before. Venkat Subramanian, he's the founder of the Agile Developer. So he graciously offered us a 1-year subscription to the agilelearner.com. So we're going to post here on the chat a link to a form. If you want to participate and we're going to do a raffle. If you want to participate in the raffle and try to get this 1-year subscription, please fill out the form. We're going to be announcing during the Q&A the winner. So now without further ado, I want to invite Ron Pressler, the tech lead of Project Loom. Ron, we're very excited to have you here. Thank you very much. I know it's late in London, so thank you very much for being here with us.
Hello. Right. Let's get started then. Okay, so I'm Ron Pressler. I'm based in London. I work at Oracle in the Java Platform Group. That is the group that develops Oracle's implementation of Java, which is called OpenJDK. And today I'm here to talk to you about Project Loom. Project Loom is an OpenJDK project, which means it's being developed separately from the JDK, which is the main OpenJDK project, with the anticipation that it will eventually get merged. In the meantime, you can download Loom early access binaries here. You can provide feedback on the Loom mailing list here. And if you want, you can take a look at our repo on GitHub. Okay. Right, so we're going to be talking a lot about concurrency, and perhaps it's best to say what it is, maybe by explaining the difference between it and parallelism. So parallelism is when we want to do one task, but we want to make it run faster. So we care about its duration, which we call latency. And we want to make it run faster, we can try to split it up into multiple subtasks that cooperate with one another and use multiple processors or computing resources. But concurrency is quite different. Concurrency is when we have many different tasks that are largely independent. They might be talking to one another a bit, but they're largely independent. The problem we're solving is managing those multiple separate tasks with our given computing resources. Usually, the number of the tasks is much greater than, say, the number of processors. So the problem with concurrency is assigning or scheduling the tasks to computational resources. And in terms of performance, the thing we care about is throughput, namely the number. So an example of a concurrent application is, of course, perhaps the canonical example, at least in the world of Java, is the server. In terms of performance, we're interested in throughput, which would be the number of transactions dispatched per unit of time. The behavior of concurrent applications, especially servers, is governed by this formula here, which is called Little's law. It appears very simple. Deriving it is actually not that simple. The thing is that it's independent of various statistical distributions. That's why it's not trivial, but understanding it is. So lambda is our throughput. That's the number of transactions that arrive at the server per second, say, and it must also equal the number of transactions we complete, because otherwise it just pile on. W is the average latency of handling a specific transaction. And L is what I call the level of concurrency. That is the number of transactions that are currently in flight, that our server is currently processing or currently handling. And if we want to increase our throughput lambda, then we might try to decrease our latency, but most of the time that is beyond our control, right? Because when we process that transaction, we might want to access some database or some other microservices, and we might not have control for how long it takes. So the easier thing to do to increase our throughput would be to increase the level of concurrency, increase the number of things we can do at once. We can look at it from the other direction and think of L as being a sort of a limit to how high our throughput can go, given some average latency, which is usually more or less constant per system. All right, so that's the background. Now, in Java, concurrency, when you speak of concurrency in Java, we speak of threads. Threads are so fundamental to Java that the entire platform is actually built around them, from the language to the tooling and all the layers of the JDK. So in the language, we have exceptions, right? And exceptions give you a context of some error. And that context is the call stack of your current thread. We have thread locals. We can associate some data with the current context, and that context is, again, that thread. When we step through our code in the debugger, say we want to trace the execution of a transaction, what it is that we're doing, we're stepping through the execution of a single thread. And when we profile Java, of course, with JFR, that's the future of Java profiling, it tells us what our application is doing on a thread-by-thread basis. So threads are fundamental to the entire design of the platform. So far, well, threads in Java are represented as in the Java lang thread class, and so far we've had one implementation. And that implementation maps one Java lang thread object to a single OS thread. So we rely on the OS we're using, whether it's Linux or Windows or Mac, to give us the implementation threads. Now, the OS is not Java specific, right? It must support all languages. And because of that, threads are very large objects. They don't know how various languages make use of the thread stack. So they need to allocate very large stacks. Also, context switching from one thread to another requires going through the kernel, which makes things a bit slow. And the algorithm that schedules our threads to our processor calls is sort of a compromise between different kinds of behaviors, right? So we could have, so a thread that handles transactions and very frequently blocks an IO is very different from a thread that's now doing some, I don't know, machine learning. So their behavior is quite different, but the OS scheduler is just one algorithm, which is a sort of a compromise between all of them. So when we write such concurrent servers in Java, and this is how we used to write them from the early days, the easiest style to do is just a synchronous, what we call the synchronous style, and that is we handle a transaction start to finish on a given thread. Now, this design, this code design is harmonious with the design of the entire language and platform and tooling, and the code is readable. It allows us to use a debugger. It allows us to use a profiler. But the number of things we can do simultaneously is equal to the number of threads. And the number of threads is equal to the number of threads the OS can give us. And because OS threads are so heavyweight, that number is quite low. Right? So if a modern server can serve, say, 1 million or even more open sockets, it can't get nearly as many threads, right? So maybe a couple of thousand active threads. And this low level of concurrency starts becoming a limiting factor. So it's a costly resource. It's very nice for the programmer, but it does not make good use of the hardware. We could handle much more, but we need to do less because we rely on the OS implementation. So as programmers, what do we do when we have a costly resource? We reuse it. And that's the idea behind thread pools. So we say, instead of creating a new thread for every transaction, we'd have a pool of threads, and every time an incoming transaction comes in, we'll just grab a thread from the pool, and when we're done with it, we'll return it. Already, this introduces a few problems. First of all, now the thread is not mapped to a single transaction throughout the thread's lifetime, right? So after the transaction finished, the same thread will be used by another transaction. And this means that if the first transaction sets a thread local, it will leak to some completely unrelated task that runs on that same thread later. So that's something we must take care of. Another thing that makes it complicated is, suppose we want to cancel a task that is running, and this is very common in servers. But because a thread can process one transaction and then there's another because they're pooled, by the time we interrupt a thread, it might be running a different task from the task we intended to interrupt. And this means that everywhere where we write code that anticipates cancellation, we must handle the case where the interruption is spurious. It's actually intended for someone else, and that makes interruption very complicated. But sorry, but the biggest problem is that it doesn't really solve the scalability issue, because at best, the number of things we can do simultaneously is the number of threads that we can have in the pool. And the number of threads we can have in the pool is limited by the number of concurrently active threads that the OS can support, which is quite low. So we're trying to do better. And we say, okay, we want to have, we want to support more transactions than threads that the OS can support at any given time. So what we're going to do is that instead of hanging on to a thread for the entire duration of the transaction, for a part of that, usually for much of that time, that thread is not actually using the processor. It could be waiting on some microservice to respond. So every time it's waiting, let's return the thread to the pool, even though the transaction is still running, right? It's waiting for something, but we want to reuse that thread in order to reuse the processor for another task. So we want to return it to the pool, not when it's finished, but every time it waits. So this solves a scalability problem, but on top of those two problems, it adds two more. First of all, the APIs, the normal blocking APIs we have in the JDK and elsewhere don't work like this, right? So if we use JDBC or some HTTP, synchronous HTTP client, those do hang on to the thread while they're waiting. So we need to use completely different APIs. Also, I mentioned at the beginning that a thread, the thread in Java really defines the context of our operation. And now, even for a single transaction, it's no longer, so if before, a thread could be used for many different transactions. So in this case, a thread can also be used for many different transactions, but even one transaction can run many different threads at different stages. So we completely lose any kind of mapping between a thread, which is our context, and our transaction, and we lose the context. So this means that if we get an exception, the stack trace won't tell us anything interesting. If we try stepping through the code in the debugger, we won't be stepping through the execution of a single transaction. If we try to get a profiler to see what our application is doing, if all of our transactions are waiting for I/O, but they're all running, we might see just idle thread pools. So in terms of usability, this is quite horrible. And this is called the asynchronous style. So it is scalable, but it's hard to read, and we lose all the stuff that we actually want from context. I say that it's disharmonious with the entire design of the Java platform, but it does make good use of the hardware. So really what we're telling developers is that you have a choice to make. Either you write your simple code, but then you waste your hardware and you have to buy more servers or rent them, in the cloud, and then you spend your money on servers and hardware, or you make good use of the hardware you have, but then you have to spend much more time on your developers, because developing the code and maintaining it is much harder, and profiling it, actually doing anything with it, is much harder. And this is quite a bad dilemma, but solving it, so you'd think that the solution is quite obvious, right? We just need to keep the thread, but allow people to have more of it. And the goal of Project Loom is to do exactly that. And we knew it was possible to do, but we didn't exactly know how. So the mandate Project Loom got from the Java architect was to rethink threading. So every time we add a new feature to the Java platform, there are two opposing forces pulling out us in two directions, opposite directions. First of all, we'd like to have forward compatibility. It means that we want existing code to enjoy the new functionality as much as we can. A great example of that is a pre-Java 8 code that used, I don't know, the callable interface, and post-Java 8, it would just work with lambdas. And that's terrific, right? You don't need to rewrite your code in some new style. On the other hand, when we have a new feature, especially something that we think is going to be popular, it's an opportunity to correct our past mistakes and maybe get rid of some old stuff we've accumulated over the years. And certainly, the thread class in Java over the years has accumulated a lot of stuff. So at first we tried various things, but we wanted to see how people use threads in Java or the thread API. And we discovered that different aspects of the API were used in different ways or different frequencies. On the one hand, thread locals and thread.current thread are very heavily used. I think one of the people on the team found out that using, I don't know, SLF4J, a single logging command called thread current thread 40 times. On the other hand, all the other stuff in the thread class is hardly ever used, especially because ever since Java 5, we've encouraged people to use Java util concurrent and to use executors and futures. So not many people actually call the thread constructor and many of the other thread or even thread join, but those are very sensible things to call. And there are many, many other methods that I hadn't even known existed. You should take a look at the thread class. I think you'll discover things that you didn't know were there. So much of it is just unused. And we also realize that now we have a new deprecation policy that does allow us to change the spec in sensible ways over time. And we could, over time, perhaps remove some of those very old methods. And the thread class itself doesn't really add much in the way of overhead, or at least we could mitigate it. So the fact that the thread class itself is kind of old wouldn't matter that much because people aren't really exposed to it. Even though they use threads all the time, they only use very small parts of it, and they're not exposed to the whole thing. So the baggage that threads add is not that great. So what we decided to do was to provide another implementation. So the existing implementation, the one that assigns a single OS thread for Java lang thread, still exists in Loom, but you can still use a new kind of thread, which is lightweight, and it's going to be represented by the same class. When you construct the thread, you choose which it is you want. And if we implement threads in Java, then we can make them much more lightweight, and you can have many more of them. The Java runtime is much better positioned to implement threads than the OS because it knows how Java uses the stack. So instead of allocating a huge stack, it can use a completely dynamic stack that grows and shrinks as needed. All the context switching from one thread to another does not require switching into the kernel. And we, instead of forcing a single scheduling mechanism in everyone, we have a good default for normal transaction processing, but if you have some special use case, you can plug your own scheduler written in Java. Okay, so what happens with these new threads we call them virtual threads. And because we're using the same thread class, you can continue using same APIs in the JDK. So some NIO, the NAO socket, or even the old java.net socket, you call some IO operation, it detects whether you're running in a virtual thread or in an OS thread. And if you're running in a virtual thread, it will just suspend that thread. It will start a non-blocking IO operation in the operating system. So even though you yourself are writing blocking code, and you're saying, I want to block and read from that socket, underneath the covers, the JDK will switch that into a non-blocking IO operation, and the scheduler is going to be free to run a different virtual thread. And when the IO completes, it will ask the virtual thread, it will resubmit the virtual thread to its scheduler to be resumed. So virtual threads are very lightweight, and the JDK doesn't have access to the actual CPU cores directly like the OS. So we sort of simulate them with OS threads that we call carriers, and we can schedule a great many virtual threads, even millions on top of a few carrier threads that correspond more or less to a single CPU core. So it's interesting to look at the course of the threads throughout Java's history. So when Java started, it was before even hotspots existed. So we're talking 1995, 1996. The Sun JDK had green threads, and those were also threads implemented in user mode, but they were all scheduled onto a single OS thread. The threads we've had since then until now, I call them platform threads, and they map one-to-one. So this is a Java-lang thread. Each of them maps to a single OS thread. And Project Loom adds virtual threads, which is many-to-many. So how have we done in terms of making the threads more lightweight? So the existing OS threads, platform threads, require about 2 kilobytes of metadata, and the default is, I think, 1 megabyte a stack. Switching between them takes between 1, even could take as much as 10 microseconds. When it comes to virtual threads, we have a couple hundred bytes of metadata, and the stack grows a string as it goes. It could be a few bytes, it could be a few kilobytes, and context switching is also faster. But of course, the main benefit of performance is just that you can have many of them, right? Remember the L in the Little's law. How do you create virtual threads? So we have a convenience method called start virtual thread, and that's it. We've also added a builder. Instead of adding more constructors, we just you get a combinatorial explosion of parameters. Instead, we just added a builder to thread. You can configure the thread and ask it to be virtual. You can create it already started or not, and you can even use the builder to create a factory, a thread factory, and thread factory is an existing interface which is used by many of the Java util concurrent executor classes. Now, it seems that all we've done is we've made threads smaller. And you might think, well, okay, so now you're taking all the problems we've had with threads and just making more of them. But that's a bit like saying that a smartphone is a miniaturized or a downsized mainframe, and all the problems you have with mainframe you have with a smartphone. Well, you might have different ones, but they're not the same ones. For example, with a mainframe, you need to take care of multiple users, which you might not with a smartphone. So the mere fact that we've downsized threads has actually solved many problems, like we've seen with thread locals leaking, and with interruption, and with losing context. So all that simply goes away just by miniaturizing threads. But still, because threads are so cheap to create now, with virtual threads, you will never ever I'm saying you never have to pull them again. So forget about, one of the funny things is that to learn how to use Loom, you don't really have to learn anything new. You just have to unlearn old habits. And one of the things you have to unlearn is that you never have to pull threads again. You just create one like you'd create a new string. Still, because people will now create many more threads, you want to do a tiny thing, I don't know, do an HTTP call, you create a new thread for it. So we thought it might be a good idea to have a way to help people organize those threads. And we found this idea elsewhere. It's called structured concurrency, not our idea. The name was coined by Martin Sostrick, but I think it was made famous by Nathaniel J. Smith in these 2 blog posts that I would recommend everyone read. You read them and you're immediately convinced that this is the right way to go. So what is structured concurrency? The idea is that every time you have a flow of a program, say this is one process, one thread, every time it splits, with structured concurrency, you have to join before you can continue. Right? So you split here, you split again. Before you can continue, you have to join. And then again. To give you an example of something that's unstructured, if you call a method and the method starts a thread and then returns while that thread is still running, then that is unstructured concurrency. Because it's like fire forget. It's like you don't know it even exists. You don't know when it's going to die. This is what people do today. And the new idea is trying to give people ways not to do it. So structured concurrency, the word structured means, similar to structured programming, it means that the runtime behavior of the code is reflected, or the runtime behavior of the program is reflected in the syntactic structure of the code. When you look at the code, you know where the control flow and the way the program is going to run. This is what, so far in a current prototype that you're trying today, this is what structured concurrency looks like. There's a shorter way to do this. I'm showing you the long form. I think in the next slide, I might have an example of the shorter one. So first we create a virtual thread factory, right? So it's a thread factory that is configured to be virtual. And we have a new kind of executor. So it's the familiar executors class in Java util concurrent, but we have a new kind of executor called the thread executor. And you might be familiar with the other executors in Java util concurrent executors, which are all thread pools. This is not a thread pool. This executor, what it does is that every task you submit to it, it will create a new thread. How will it create a new thread? It will use the factory, and this factory creates virtual threads. So every new task you give it will create a new thread. Nothing here is pooled. So we submit a task, we submit another. Because we're using this executor, these will spawn new threads, and these threads will be virtual. Now we're doing this inside a try with resources block. This is new. We've changed, this returns an executor service interface. We've changed it to implement auto-closable, so it can be used inside try with resources block. And what the close method does is that it waits for all the tasks to complete. So these will actually create new threads, and we won't be able to exit this block until all both of these tasks will terminate. How does this help us? So many times when we write servers, we might want to do some operation and give it a timeout. And this could be quite complicated because we have to thread the timeout throughout all of our calls, and maybe sometimes do some arithmetic on the time that's remaining. What this allows us to do something very simple. We create this executor and we give the entire executor a deadline of now plus 30 seconds. And then we submit those tasks and we wait for them to terminate. If they're both terminated before the 30 seconds have elapsed, we just continue. If not, or if one of them hasn't, we cancel them. We interrupt the threads running them. But either way, we can never exit this block until everything that exists inside it is dead. So once we're outside, we know that these things are finished. Of course, what happens if we want to collect the results? So we've added some nice combinators. So one is called invoke any. We can give it a list of tasks, and invoke any says, give me the results of the first task to finish successfully, so without an exception. And here I'm using the shortcut new virtual thread executor, which is the same as doing new thread executor and giving it a virtual factory. And this will submit these 3 tasks. So in this case, it will create 3 virtual threads and will assign the results of the first one to complete successfully into first. If none of them do, it will just throw an exception. And we have a similar combinator called invoke all that collects all the results. And I think that with that, I am done. I'm happy to take your questions.
All right. Thank you. That was a great presentation. I hope everybody's as excited as we are with Project Loom. I just want a quick reminder, please use the chat if you want to participate in the raffle. The link is on the chat. And Jean, I would like to call you to do the Q&A. I don't know if Jean having any issues. So let me ask you the first question. Are there any limitations today with the lightweight threads? Can it do whatever a regular thread does, or there are any limitations?
No, it can do anything. There are a few things you might want to. So it behaves the same way as an OS thread, but there are a few things you might want to be aware of. One is that if you call into a native method with JNI, and that method does IO, blocking IO, then we won't be able to suspend the virtual thread. It will just hang on to its carrier heavyweight thread. And also we have so that limitation is here to stay forever. It's just not very common that people do blocking IO inside JNI. A temporary limitation is that if you're holding onto a native monitor, so that is if you're inside a synchronized method or synchronized block and you're doing blocking IO, that would otherwise just suspend the current virtual thread. We don't currently suspend the virtual thread, but actually the underlying kernel thread. So if you do that, you won't get the same scalability benefit. I wouldn't worry about it too much. It should only matter if it happens extremely frequently, and we will have diagnostic options that tell you when this happens, and also we hope to be rid of this as soon as possible. But if you're using Loom and you're doing IO, blocking IO inside of synchronized blocks, and it's very frequent, you might want to reconsider using one of the Java util concurrent locks instead, like reentrant lock or stamp lock.
Thanks, and thanks, Rodrigo, for covering there. What's the difference between green threads and virtual threads?
Between green threads, yeah. So green threads, they're both user mode threads, but green threads used to be scheduled onto a single OS thread. So they were a single call. Virtual threads are many to many, and they also allow you to plug in your own scheduler. So okay. It's the same general idea, just a different implementation.
Our next question, which got asked by several people, is when can we expect to see Project Loom and what version of Java is it in?
we don't know as soon as it's done. I can tell you what it is that we're working on. So right now we have, in terms of functionality, we're more or less done. But, let me stop sharing the screen unless somebody, I can re-share again. In terms of functionality, we're more or less done, but we still have quite a few stability issues that we have to solve. There's some very strong interaction with the various GCs, and we have to make sure they all work. This will take some time. We have to port this to ARM64. Right now, we're just on Intel x86 64. We still have some work to do in terms of debugger support. And one piece of functionality that's missing is that if you try to get a thread dump, we don't yet know what is the right way to present the stacks of 1 million threads. We might want to collate them in some way, perhaps arrange them in a tree based on structured concurrency. I would say that's the one thing that we still aren't sure of in terms of design. But as soon as it's on, I don't know what version it's going to be.
Sure. So we've hopefully all moved from threads to executors and possibly scheduled thread pool executor. Is there anything you can do with executors and Loom so that you're using your executors for virtual threads versus, traditional heavy threads?
They'll be used the same way. The only thing is that you need to use, you mustn't pool virtual threads. I mean, you could, it just would not be a good idea. So you'd want to use executors new thread executor or new virtual thread executor. So just don't pool them. You don't want to share virtual thread because there's just no need.
Has the Spring ecosystem been involved in this so that Spring Boot will be able to use the performance benefits from Loom without developers having to change their code?
I don't know, but I assume so. Normally, I think they try to take advantage of whatever it is we put in the JDK, so I don't think this would be an exception.
Okay.
I do know that we ourselves have done some demos, not with Spring, but with Jetty and Helidon. Just demos, but I guess the Spring team will support Loom eventually.
Can you talk about what people should expect with respect to performance and if it differs based on your operating system or device?
I don't think it should differ based on your operating system or your processor. In terms of performance, the goal is to be on par with non-blocking asynchronous code today, but while running synchronous code. If you see that it's not that, so if you use some reactive framework and you see in some real time, it's easy to manufacture workloads that, in various micro benchmarks benefit one thing or another. But if you see in some normal workload, an actual difference between some asynchronous framework and Loom's virtual threads, let us know about it because the goal is for it to be the same. So you'll get the same performance as asynchronous code while writing synchronous code.
It's funny that you mentioned blocking because we got a question of blocking. Will File I/O be able to take advantage of Loom in any way?
Great question. So there, so it is a great question, but unfortunately, this is a part of the project. So in terms of actual programming, I do stuff inside hotspots, and other people do stuff in the core libraries, and this is a core libraries thing. So I know about it, but I'm not an expert on it. So most operating systems don't actually support good. They don't have good asynchronous APIs for file I/O. When they do, for example, Linux has IOUring. When they, I know to say the name. I don't know too much about it beyond that. So the goal, at least for Linux, is to give you async. So when you'll do blocking file I/O on Linux, it will use IOUring under the covers. I don't know if it's going to be in Loom's first release or later on. But operating systems that do not support asynchronous file I/O, what's going to happen is that the underlying kernel thread will be blocked, but the scheduler will compensate by starting more worker threads. So I think that current implementation uses the managed blocker mechanism in order to compensate for file I/O. I do wonder, though, how common it is to do a lot of file I/O for 1 million concurrent tasks. So if you have a workload that needs that, let us know, just out of interest.
So since you brought up let us know, how does one let you know?
On the Loom, let me share that again. We have this mailing list.
On the mailing list that was on the slide before.
Yes.
Also, I think you might be breaking labor laws because Duke's been working on Loom for a really long time there. Got to get breaks. We'll leave the mailing list up so that people at times they screenshot it or take a picture on their phone or whatever. Also, you're talking about implementation. What can you tell us about how lightweight threads were implemented in the JDK?
Wow. Okay, that's a whole other talk. I'll just give the highlights. So a thread is really split into two capabilities. It needs the ability to run a piece of code, suspend it, right? So when you do I/O, what is it that you want from a thread? You want it to be able to run, do some I/O. While it's doing I/O, you want it to vacate the CPU. You want so that something else could run on it, and then you want it to be able to resume. So the first capability is to be able to take a computation, suspend it, redefine its state, and resume it later. Most of its state, of course, is the stack. So the state of the thread is the stack. The second capability is a scheduler. So you want some process, some algorithm that decides which thread to run when and where. So obviously the thread has to be runnable. It has to say, I'm not waiting for anything, I'm done, please run me. And then you need an algorithm to say, okay, now I'm going to take you and run you this processor. So the first part is called a continuation, and the second part is just a scheduler. Continuations were added into Hotspot as an internal mechanism, like AGC, and they're exposed to the JDK libraries as a very thin API, and then most of virtual threads are implemented in Java in the libraries using Hotspot's continuations, and the virtual thread scheduler can be actually any Java util concurrent executor. So you can write your own. It's very simple. And the way, and the executor doesn't even need to know that the task it's executing are virtual threads. It just gets runnable, it runs it. But if it's a virtual thread, and that runnable, when you run it, it won't start from the beginning, but it will actually continue from where it's suspended. So that is how we've implemented.
Cool. In the effective Java book, one of the items is prefer executors, tasks, and streams to threads. Where would you stick virtual threads and Loom in that list?
So still, you will still use the executors class. Let me go. So You would use executors. Just use this one, new thread executor, new with a shortcut, new virtual thread executor, and then just use executors.
So would you put that above the traditional executors, that you'd use this one instead of the ones we're using now, or it depends on what you're doing?
Yes. Instead of, I don't know, new pool, thread pool, something executor, just use this when you're using virtual thread. A question you didn't ask, maybe not yet, but might be a good time to address is, why would you ever use the heavyweight OS threads? So you should use this only when you want to use virtual threads. Why wouldn't you? So virtual threads are very good for transaction processing. If you have lots of different tasks that very frequently do some small bit of processing and then they block. So something that does I/O, something that reads messages off a queue like an actor, responds to messages, that is great for virtual threads. But if you have a thread that, I don't know, inverts a huge matrix or encodes a video or does some, a lot of processing that's not necessarily intermittent, you might want to use an OS thread for that.
Okay, cool. At this point, we're going to take a 1-minute break. So if you want to have a drink of water, Ron, you have it. We're going to announce the winner of our contest. This is a must be present to win thing. So I'm announcing it early to give you time to put your answer in the chat. If I say your name, please post in the chat in order to claim your prize. The winner is Masood Parvari, MASOUD Post in the chat to say you acknowledge this, and then you win. If you don't post in the chat, I will draw another winner later. Back to our regularly scheduled Q&A. I hope you enjoyed your 1-minute break, Ron. Our next topic is about security.
It was less than 1 minute.
Oh man, I talk too fast because I'm a New Yorker. But New Yorkers are also very big on security because there's a lot of financial institutions in the area. Is there anything we need to be conscious of for security with Loom? For example, having a spammer spin out 1 million threads for evil is a problem, and we don't want problems to happen.
That is an interesting question. I'm not a security expert. I wouldn't think that it would be any different than, if you just use some asynchronous code and the attacker would spawn 1 million transactions. So it should be similar, but I'm not the one to ask about security.
Okay, that's fair. So ask your local security expert. And our winner did claim his prize. Congratulations to our winner. Our next question is, do you have any control over how many CPU cores are used by virtual threads in Loom?
Yes. So when you create a virtual thread, by default, it uses a default scheduler. The default scheduler is a fork join pool, and it's its parallelism, or the number of cores it uses, can be set by a command line flag. But so you can either use a default scheduler and set the command line flag to your desired parallelism, or you can just apply your own scheduler. It can be a fork join pool, or it can be something else.
Are virtual threads meant for I/O bound processes and regular threads meant for CPU bound processes, or something else?
What was the first part?
Are virtual threads meant for I/O bound processes?
I/O. As a general rule of thumb, I would say yes, but it's not necessarily I/O. So yes, I/O bound applications, I'd say. The threads themselves can be very, very small. So in the course of processing a transaction, a small bit can do I/O, and then, I don't know, put a message in a queue somewhere, send a message to an actor, and then the actor would respond. So it's anything that blocks very frequently or is very intermittent. So anything that does a lot of I/O, a lot of message processing. But as a general rule of thumb, if you are CPU bound, yes, then virtual threads are not going to help you.
Okay. On a lighter note, you use the phrase harmonious concurrency. Is that a reference to Martin Thompson's mechanical sympathy?
No, but I guess it could be.
It is now, right?
Harmonious.
It was a nice alliteration.
Yeah, but so it could be. So mechanical sympathy is about being harmonious with the hardware. And when I say harmonious concurrency, I mean being in harmony with the design of the platform. And all the tooling, all the language, the libraries, are all designed around the idea of thread as context. And once you move away from thread as context, and for good reasons, you know, people use asynchronous code because if they were to use a thread per transaction or the thread per request model, that would just wouldn't scale well enough.
Right.
So when you move away from that, you're starting to fight against the grain of the platform itself. So with virtual threads, you're harmonious with the design of the platform, which is around threads. You're harmonious with the way the code looks. So you can use control structures, you can use exceptions. You're harmonious with the debuggers. You're harmonious with the profilers.
Will a thread know whether it's in a virtual thread or a kernel thread?
Well, code no,
When
yes.
you're writing code, will the code know where it's running?
Yes, although, yes, so you can do thread.current thread.is virtual. Currently, it might be split, although I would say that code smell, the only place where such a check should appear is inside low-level synchronization construct. So inside Java util concurrent, say reentrant lock, it would make sense to say that a virtual thread and a heavyweight thread, a platform thread, have different spinning strategies. So because a platform thread is very costly to block, so you'd rather spin for a bit, but because a virtual thread is very cheap to block, you don't want to spin and just hang on to the CPU. You want to release the CPU to another thread, and that would make sense for is virtual to appear there. But I don't think it's a good idea for it to appear in user code. Again, if you think it should, let us know. It's available, but I would say it's a sign of some code smell.
That's good to know before we start typing it into our code. Yeah, think a million times if you're doing this.
Well, if you do think you need it, let us know why. I don't see why code should be agnostic to the thread implementation. If you think it shouldn't be, let us know why.
Okay. Can a lightweight thread do everything that a regular thread can do, or are there limitations?
Yes, it can do everything a regular thread can do. But I think I mentioned before that to get the full scalability benefits, there is a limitation that if you do I/O inside a native call through JNI, it will block the carrier thread, and that limitation will stay forever. But a temporary limitation is also if you do I/O while inside a synchronized blocker method, that will currently also block the underlying carrier thread. I think it will compensate by adding more threads, but if you want to take full advantage of virtual threads right now, try to replace, don't do it everywhere. So some people say, okay, now we need to replace all of our synchronized with reentrant lock. Do it only when you're doing I/O very frequently. And I think we'll have some diagnostics to tell you where that happens, and hopefully we'll remove that problem in the future. We're working on it already. It's just that we're not going to wait for it. If it's done by the time the rest of Loom is done, then great. If not, we'll just release Loom without it.
Well, yeah, you can release every 6 months. No reason to wait.
Exactly.
Our next question is, what about bulkheading? Can we reserve resources for specific virtual thread factories? And I have a question, which is, what is bulkheading?
I'm not sure.
Okay. I just assumed it was a common concurrency term.
I think it's yes, it's a pattern, kind of like what do you call it? I forget the name the other one too.
Okay. No worries.
Yeah,
Next
so
question.
maybe tell the asker to the person who asked this to.
Yeah. If you ask the question about bulk heading, please ask it again with more words, and I will re-ask it to Ron. The next question should be easier. Other than just to reinvent thread, what was the underlying reason behind doing Loom? Was it for faster I/O or was it for something more?
It was to solve the dilemma between wasting hardware and wasting developers. So you had to make a choice either to make your code scalable or to make it harmonious with the platform. And this was to let you have both.
Okay.
So if you come into it, so if today you've chosen to write very simple harmonious code, then what you'll get out of it is performance or scalability. If what you're doing today is writing asynchronous code, then you won't get performance from Loom, but what you get is more harmonious code.
Okay. So does that mean that synchronize, wait, and notify work with virtual threads?
They do work, but as I said, they could. I'm trying to be careful because people think that they shouldn't use synchronized. Synchronized works, and you can use it. Just that if you use it very frequently and do I/O inside the synchronized block, then it will block the underlying kernel thread and reduce your scalability for now. That is a temporary limitation. So if you want to take full advantage of Loom, in those specific areas, you might want to replace synchronized with re-entrant lock or stamp lock. You don't have to do it everywhere.
Okay. How do futures fit into the new programming model?
So there is no new programming model. You already know how to work with virtual threads. But you know, let me share the screen again. Again, structured concurrency is a sort of a new programming model, but right. So so every time you submit something, it returns a future, and then it might make sense to get these two futures here, and then if you want to look at the result, just do a get in both of them, or we might have some other combinators. So use futures the same way you do today.
Okay, that seems easy enough. Just do what you've been doing. Would stack traces continue to be similar to regular threads with virtual threads? And is there anything we should know about changes? For example, when lambdas became a thing, stack traces got interesting.
Well, a virtual thread is a thread from the perspective of Java, at least, not from the perspective of the operating system, but stack traces will be the stack trace of the virtual thread. Will they get interesting? Yeah, I guess the bottommost calls will look different on a virtual thread because the methods. So I think today it starts with a thread.run. There might be more methods for virtual threads at the very bottom. But you shouldn't really depend on specific things. That's not part of the spec. We're mentioning before the presentation started, we were talking about the spec. You shouldn't rely on details of the stack trace because that's not part of the spec and it could change. But as a general rule, yeah, the stack traces will be the same.
Got it. Thank you. We're going to go back to the bulk heading things because Tomer provided more information. And thank you, Tomer. I tried Googling it, and bulk heading means two completely different things in computer science, which is awesome. So in the context of the question, bulkheads is a stability pattern for reserving resources for a task-specific purpose. For example, transactions handling a specific type of job won't use all of the resources, platform threads, so that other types of jobs can still do work. In the past, thread pools were used for solving that. The question is your thoughts on doing the same for virtual threads. Can we assign a group of real platform threads for a virtual thread factory to continue to isolate them?
Yes, but it's funny that this has happened to me throughout my career. But whenever you introduce you, the first thing people want to do is something very complicated. So I would suggest, I'll give a general recommendation. I don't know if this counts as blockheading or not, but today, what some people do is that when processing transactions, they have these, I think it's called CEDA or something, they have these stage architecture where it's a pipeline. So every transaction starts by doing, I don't know, parsing, and then it calls the database, and then it calls something else. And at every stage, the task moves, or the next part of the task moves from one thread pool to another. And people limit the number of tasks that can do, that can use the resource associated with that stage by limiting the thread pool. A much better way to do that generally, and it becomes free with virtual threads, is instead of having multiple thread pools, just assign a semaphore to each of the resources. So say on your database, say you don't want more than 100 more than 100 concurrent database requests in flight. So just put a semaphore, and the 101st virtual thread that will try to get to call the database will just block and wait. This will sort of do behind the covers exactly what you're doing today manually with multiple thread pools. I guess you could assign different virtual threads to different schedulers, and those schedulers would use different thread pools. I don't think this will be very helpful. So I would say start relying more on semaphores rather than multiple thread pools. Okay.
And to be fair, we did tell people to ask their hardest Loom questions, so I'm not terribly surprised that you're getting questions about complicated scenarios here. I think you've answered this, but just to confirm, completable futures will work out of the box. You don't have to do anything special.
Yes. Well, okay. So completable futures work. The thing is that you won't need to use, so I think completable future has like, I don't know, 700 methods. I'm exaggerating. It's about 70, some unreasonable number of methods. You will probably not need to use any of them except for get, because most of them, unless you want to, but most of them are designed to do asynchronous programming. So that you do, I don't know, then apply, then compose, I don't remember all the names, but with virtual threads, blocking, so calling completable future or even regular future .get, which is the most expensive thing that you shouldn't, that you should never do today, becomes essentially free. So instead of doing something completable future, first task, then compose something else, what you can do is to use a future, do a get, and then just do something else. So it works the same way as before, but you might not need to use most of it. So again, the general lesson here is that learning to use Loom is mostly about unlearning old habits. And so if you do anything about concurrency, perhaps you should ask yourself, why am I doing this? And am I doing this because blocking is expensive, or because threads are expensive? Because if that's the answer, you might want to reconsider and think, maybe I don't need to do this, and maybe something very simple will do. And in fact, try to think like, how would, a beginner or a programmer in 1995 just learning about Java and threads, how they would program, and the code would be much more simple, but it will be as performant as the most complex code you could write. And that's what Loom does. So try to simplify.
Okay. On the topic of threads being heavy resources, are virtual threads going to have their own stack like virtual threads? And if yes, what impact does that have on the stack size you set up at JVM Startup?
They do have their own stacks, but those stacks are completely dynamic. What you set at the JVM Startup will have no effect. It will have an indirect effect. I'll get to that. But virtual threads, their stacks grows and shrink according to how much they actually use.
Okay.
So you don't need to think about stack sizes. You don't need to think about pool sizes. So all that is done for you. When I said there is an indirect effect, again, just for people who want to know how stuff works under the covers, the virtual thread stack will not be able to grow beyond the maximum thread stack that you set. But for platform threads, the thread stack that you set will be the thread stack. For virtual threads, it will grow and shrink, but it can't grow beyond that. So it becomes like a maximum stack size.
Okay. We got a nice lightweight question. Hopefully this isn't your password for anything. What is your cat's name?
Oh, I have 3 cats, but the black and white one is called Schiff.
Nice. She's cute. Can virtual threads be used with JNI code that depends on OS threads?
Can
virtual threads be used with JNI code that depends on OS threads? For example, non-type 4 JDBC drivers?
It depends what used means. You can certainly call JNI on virtual threads. As I said, you shouldn't do I/O. If you do, you're kind of missing out. So I think in this case, doing a JDBC driver with JNI, I know, for example, that the Oracle database driver is written entirely in Java. But if you do, but other than that, if you call into JNI, so let's say you're not doing I/O. If you call into JNI, what you will see in your, I don't know, C or Zig code, Zig is my new hobby, what you will see is that the identity of the current pthread will just be different, right? But I guess you'd see the same if you just call JNI on tasks that move from one thread to another. Yeah, so from JNI, you won't see, unless you call the Java API, the Java JNI API. If you just try to access the thread identity, you'll see whichever OS thread you're running on.
Okay, cool. Do you see anything changing with reactive frameworks with the advent of Loom? Will reactive still be relevant?
So it depends what you mean by reactive. If you mean like a platform, a framework that helps people, that gives people high level constructs for writing bulkheads or something. So if you want bulkheads or then there will certainly be room for frameworks and third-party libraries to give higher level constructs above Loom. Will they look like they do today around what are they called? Something streams, reactive streams. I'm sorry, it's just very late. I don't think so. I mean, those new reactive frameworks would not look the same. Those people who actually really like those reactive frameworks will, of course, be able to use them. But one of the reasons we did Loom, or we thought it was urgent, is because reactive is unbelievably unpopular. People don't want to use it, and even people who use it and are sort of happy with it are really not. So I would expect to see, I mean, it's not up to, if you like it, I'm not going to tell you not to use it, but if you're asking me what I expect to see happening is that people not use asynchronous code, but perhaps those same people who give you your reactive framework, I don't know, flavor of the day, the one that you like, they might give you a new library which they call reactive, but it will look different because it will be synchronous rather than asynchronous.
Okay. We have 2 more questions and then we will let you go to sleep. Thank you for staying up for us. The second to last question is, does using synchronize lock the physical thread when you're using a virtual thread? And if so, will it be easier to hit deadlocks?
Synchronize will be easier to hit deadlocks. No, much of the time synchronize doesn't do anything. That's why synchronize compiles down to something. What you see in your code and what the JIT actually executes, and then what the CPU actually does is not the same. This is why I think it's true for everything. You know, even today, even machine code is high-level programming. It's more of a suggestion to the CPU. It's all done in microcode. But especially if you're using Java, where there's so many layers of optimization, the best thing is not to overthink it. People try to. It's not C, and even C is not what it was in the 1990s. Synchronized can, if there is contention, then yes, but again, it's temporary. So in the current prototype, if you hit contention, then there will actually be a lock held on the current kernel thread, which is why we can't release it when we do I/O. We hope that to go away. But if you're just doing synchronized around RAM operations, like a synchronized map, of course, you should use concurrent hash map. But if you are using synchronized map, there's no reason to replace it with anything else. Your level of contention and the amount of time you need to wait for that lock is probably going to be minuscule if it's not optimized away completely.
Okay. And the last question is, if people are only going to remember one thing you said today, what do you want them to tell their coworkers about Loom?
Wow. They should reevaluate their position towards simplicity and go back to simpler is better.
That's a good one. Now we're going to turn things over to Rodrigo for some closing remarks.
All right. Thank you, Jean. All right. I want to thank you all, raffle winner Masood Parvari, and thank you, Venkat, for offering the subscription of the Agile Learner to NYJavaSIG. Thank you very much, Venkat. Congratulations, Barry, for the nomination to the Java Champions Group. Very well deserved. We're very happy for you. Our next event, December 15, with Nate Shuda, and we're going to be talking about cloud native applications. So if you want to be notified, here's our website, nyjavasig.com, and on Twitter, you're going to be notified of our next events. And Ron, in the name of NYJavaSig, thank you very much for being here with us, for taking the time to be here. It's 1 a.m. It's very late. Sorry for taking keeping you awake. But we're very happy. I think everybody is very excited for Project Loom, and it's great that you could be here with us today. Thank you very much.
Happy to be here.